At Harvard, a Danish scientist, Lena Howe, had the idea of using a condensate to slow down light.
We all have this sense, light is something that nothing goes faster than light in vacuum. And if somehow we could use this system to get light down to, to a human level, I thought that was just absolutely fascinating.
Lena Howe created a cigar-shaped Bose-Einstein condensate to carry out her experiment. She fired a light pulse into the cloud. The speed of light is around 186,000 miles per second, but when the pulse hits the condensate, it slows down to the speed of a bicycle.
So the light pulse might start out being 1 to 2 miles long in free space. It goes into our medium, and since the front edge enters first, that will slow down. The back edge is still in free space. That'll catch up, and that'll create that compression, and it'll end up being compressed from 1 to 2 miles down to 0.001 micron or even smaller than that. You could say, well, gee, it's easy to stop light because I could just set a laser beam into a wall and I would stop it. Well, the problem is you lose the information because it turns into heat. You can never get that information back. In our case, when we stop it, the information is not lost because that's stored in the medium. And then when we have time to revive it, the system has all the information to revive the light pulse and it can move on.
One day, ultra-cold atoms will probably be used to store and even process information. Even now, cold atoms are being turned into prototype quantum computers.
As a quantum mechanic, I engineer atoms. To make a computer out of atoms, you have to somehow get atoms to register information and then to process it. Why build quantum computers? Because they're cool. It's fun. And we can do it. Right? I mean, we actually can take atoms, and if we ask them nicely, they'll compute. That's a lot of fun. I mean, have you ever talked to an atom recently and had it talk back? It's great. Yes, look at that.
Unlike ordinary computers, where each decision is based around a bit of information and is either a 0 or a 1, in the quantum world, the rules change.
At first glance, a quantum computer looks almost exactly the same. But quantum mechanics is weird. It's funky, okay? It's weird.
When you do quantum computing, you want to make this weirdness work for you.
So now let's look at our quantum bit, or qubit.
A qubit can not only be a 0 or a 1, it can also both be a
0 and 1 at the same time. It's almost like a form of parallel computation, but in a parallel computer, one processor does this, one processor does that. So you have two processors doing this and that. In a quantum computer, you have only one processor that's doing this and that at the same time.
Today, computers are limited in the amount of information they can handle by the heat and number of the circuits. Here, within a giant Dewar flask, lies a prototype quantum computer surrounded by its supercooled, superconducting magnet. In the future, quantum computing could be used to predict incredibly complex quantum interactions, such as how a new drug acts on faulty biochemistry, or to solve complex encryption problems like decoding prime numbers that are the key to internet security. Already, supercooled quantum devices are mapping the magnetic activity of the brain. Often, the promised benefits from a scientific breakthrough take a long time to emerge. Many predicted that by this century, energy-saving superconducting power lines and maglev bullet trains would be crisscrossing the continents. Perhaps as world energy supplies decline, these technologies, once seen as too costly, will start to take off. This weird quantum world is part of a new frontier opened up by the descent towards absolute zero. it's been a remarkable journey for scientists into unknown territories far beyond the narrow confines of Earth. On the Kelvin temperature scale, which begins at absolute zero, the temperature of the Sun is around 5,000 Kelvin. At 1,000 Kelvin, metals melt. At 300, we reach what we think of as room temperature. Air liquefies at 100 Kelvin. Hydrogen at 20. Helium at 4 Kelvin. The deepest outer space is 3 degrees above absolute zero. But the descent doesn't stop there. With ultra-cold refrigerators, the decimal point shifts 3 places to a few 1,000ths of a degree. And laser cooling takes it down 3 more places to a 1,000,000th of a degree, the temperature of a Bose-Einstein condensate. With magnetic cooling, we shift 4 more decimal places until we reach the coldest recorded temperature in the universe, created at a lab in Helsinki, 100 picokelvin, or 1/10 of a billionth of a degree above absolute zero. So, will it ever be possible to go all the way, to reach the holy grail of cold, 0 Kelvin?
Getting to absolute zero is tough. Nobody's actually been there at absolute 0.000000 with an infinite number of zeros. That last little tiny bit of heat becomes harder and harder to get out. And in particular, the timescales for getting it out get longer and longer and longer, the smaller and smaller the amounts of energy involved. So eventually, if you're talking about extracting an amount of energy that's sufficiently small, it would indeed take the age of the universe to do it. Also, you actually need an apparatus the size of the universe to do it, but that's another story.
Absolute zero may be unreachable, but by exploring further and further towards this ultimate destination of cold, the most fundamental secrets of matter have been revealed. If our past was defined by our mastery of heat, perhaps our future lies in the continuing conquest of cold.